Okay, now how do I go about making a compensator out of this TL431 or LMV431? Well, we know that the standard circuit for a type 2 compensator, it looks like this. We know that the 3-pin reference can be made to look like exactly this op-amp with an internal reference. So let's have a look at what happens. This is a standard textbook type 2 op-amp. This is the reference pin of LMV431. This is the anode pin of the LMV431. And this is the cathode pin. Okay, so now let's compare this to the actual device. There we go. That is the device like it's shown on the date sheet. That is the reference pin. That pin is the same as that point here. Then that's the anode pin. That pin is the same as that point here. And this is the cathode pin. That is the same as that pin here. So all I have to do is to make a type 2 compensator is to just connect it exactly the way that that circuit looks. So first I will make this potential divider, which is exactly the same as this. Then I will connect the compensation component. Please have a look at this. It's exactly the same as that, and I'm done. When you look at this on a data sheet of a device, it kind of looks a little bit intimidating because you look at it and just think, oh, where will all of these, where are these components are coming from? But in reality, that is just that op-amp. So you haven't invented anything difficult. It is just what we have always been doing. It's a type 2 compensator. If I wanted a type 3 compensator, all I have to do is to add a resistor and a capacitor across here, and then I have got a type 3 compensator. There you go. That's a type 2 with LMV431. So now that we know how the TL431 works and how it looks just like an op-amp, we can now start designing. Here I have got the transfer function of a standard type 2 compensator. Yeah? And here I've got the equations for the type 2 compensator for an opto-isolated power supply. We discussed the bandwidth of the opto-isolator. We represented it with C opto, and we also said that this represents a pole between R pull-up and C opto. And I can change the position of this pole by adding some capacitance across here. So I've got some control over the pole that this is creating for me. So the equations that you see is extremely similar to what you have on a standard op-amp with a standard component. It's just that now you have got an optocoupler in the middle, but we have characterized it. Again, there are some excellent references by Christophe Basso on how this whole thing works. You've got the transfer function. You know the position of the 0. You know the position of the pole at origin. And you know the position of the second pole. So you can pretty much calculate everything. You can decide on, when you calculate the position of the pole at origin, the position of the 0, and the position of the second pole, then all you have to do is stick them in these equations and you end up with component values. The pull-up comes from the IC's internal reference pin. In our case, for the one that we're going to use in the lab, it's 8 volts. VCE is fed back to the controller. C opto is the parasitic capacitance that we measured using the opto-isolator. And one thing that we must do in order for everything to work is to cut the fast lane. Again, this is something that was proposed by Mr. Basso. If you look at this, you will see that, ignoring this Zener here, you will see that any change on the out will immediately change the current through the diode. And that Mr. Basso called the fast lane. I understand that he was the first person to use this terminology. So that is the fast lane, And that is going to mess up all of these beautiful equations that I have created, and all these transfer functions and all this analysis. This one, when Vout changes here, it's going to change this, go through the time constant of that, get past the optocoupler, and this one is called the slow lane. So I've got a fast lane and I've got the slow lane. All of these equations are based on the transfer function of my optocoupler RC around here. However, this fast lane is absolutely messing everything up, so I need to cut it. How do I cut it? Well, I get a Zener, I operate it in breakdown region, and that way the voltage here will remain constant when this thing moves up and down, and that is how you cut the fast lane, and then all of these equations become valid. That was a type 2. Finally, let's have a look at a type 3. Transfer function is exactly the same. The equations for the polar origin 1, 0 and 1 pole are exactly the same. All you're doing is you're adding a capacitor and a resistor, and these now add an extra pole and extra 0. So this and this. The rest is actually identical to the type 2.